Okay, so let's get started, please. So remember what we were talking about? We were talking about how to parameterize surfaces, right? Talking about parametric surfaces, right? And the next thing we're going to do is talk about the surface area of a parameterized surface. Okay, so finding the area of a parameterized surface. Yeah, I should say that my wife has forbidden me to ever do this surgery. She says, "You have family now, that'd be great." Okay, so here's what we're going to take as the definition. And it's not really satisfying as a definition, but that's what we're going to use. So if you have a parametrization, a smooth parametrization of a surface S, then we define the surface area of S to be the integral over the domain against area of the partial with respect to the first variable crossed the partial with respect to the second variable, and you take the magnitude of that. So you take the tangent vector along one grid line, you take the tangent vector along the other grid line, you cross those things, and then you take the magnitude of that, and you integrate that over the domain. And that we say is going to give you the area. So just to show that this is not completely implausible, let's look at the surface area of a sphere. So let phi theta range over 0 pi cross 0 2 pi, and we'll use spherical coordinates phi theta. So sine phi cosine theta, sine phi sine theta, cosine phi. Right. This is the these are the Cartesian points corresponding to the point on the unit sphere, right? With spherical coordinates phi 1 phi theta. Right. And so we'll take the tangent vector by taking the partial with respect to the first variable, right? And you get cosine phi cosine theta, cosine phi sine theta, negative sine phi. Take the partial with respect to theta, and you get negative sine phi sine theta, sine phi cosine theta, 0. And then when you cross them, r theta cross r phi, you end up with negative sine phi times cosine theta sine phi sine theta sine phi cosine phi. This thing on the vector part of this, you see, is a vector on the unit sphere again, and so the magnitude of this is just going to be sine phi, or the absolute value of sine phi. And then, so So calculating the surface area. So the surface area then is going to be the double integral of absolute value of sine phi dA, right? D theta d phi, as phi goes from 0 to pi, and theta goes from 0 to 2 pi. Everyone okay with that? Right? We get, right, this thing is gonna be this thing dA over this thing, right? Right? So we're integrating this as, theta and phi range over this, and so we just, you can do it in whatever order you like, right? So we're gonna take d theta d phi. Doesn't matter. Okay, so 0 pi, 0 2 pi, right? And you notice that sine phi is always going to be positive in this range, right? As phi ranges from 0 to pi, sine, sorry, this goes from 0 to pi, then sine is always positive, right? So we can get rid of this. Right? When you work it out, you get 4 pi. Cosine phi from 0 to pi, that gives you 2, right? And then you got this 2 pi here, so you get 2 times 2 pi, that's 1 pi. Okay, so that's right. That actually is the area, the surface area of a sphere with radius 1. So, any questions? Yeah. Okay. Simple. I'll let you do one for practice. So here's an exercise. Find the area of z equals 2/3 x to the 3 halves plus y to the 3 halves. So here's the graph of some function, right? As x and y range over the unit cube. The unit square. So just take a minute or two and set up the integral. So it's going to be integral of something dA dx dy, so as y goes from 0 to 1 and x goes from 0 to 1. Okay, so just figure out what you need to integrate. Okay, so turn to somebody next to you and say what your parametrization is. And what your tangent vectors are.
That's what I did, but then not do things, right?
It's like that you don't just see in concepts.
Yeah, when you, like, if you just take the potential. Yeah, but it's supposed to be, they're supposed to be vectors. Oh, I know, I did this something. It's like, so it's U, I, plus V, J, plus, then you do this whole thing, so then it's 2/3, x to 3.5, plus y.
Oh.
Well, actually, this is U and V.
Okay, so what are you guys using as your parameterization? R of x, y. So.
And then.
What are you taking as your parameterization?
X, y, and then 2/3 x to 3.5 plus.
X, Y, Z. And then you take your partial, take the tangent vector, along the x grid line, right? So you get 1, 0, x to the 1/2. Tangent vector on the other, you're going to get 0, 1, y to the 1/2. Right? You cross them, on x cross on y, gives you, so you can see it, so negative x to the 1/2, y to the 1/2. Negative, right? Yeah. Negative y to the 1/2, and then 1 over. Right. Okay. So then the magnitude is going to be the square root of x squared plus y squared plus z squared, everything to the 1/2, and so that's what you're going to integrate. And that would be that whatever that is, that will give you the implicits. Okay. So what is this? What is this RU, RV, VU, If you think about it, here's your domain. Here is D. And you divide, as usual, you divide your domain into pieces, right? And you have some point, and then you have this little box here, and the width of the box is delta U. The height of the box is delta V. Okay. And so R, right, is your, just to give you an idea what's going on here, right? R takes, R is the parameterization of this surface S, right? It takes D to here. Right? If you take RU, right? That's the that is the slope, right? That is the tangent vector. So let's take this point. Let's say that this point is R of this corner here. Then R sub U is going to be the tangent vector along in the U direction. Let's say that these things are the grid lines. Okay. So here is R sub U, and then R sub U is this thing, R sub V is this thing. Right? You get these two tangent vectors. Right? and multiplying them by, so these are like velocity vectors, right? And then multiplying them by delta u and delta v, right, give you some sort of parallelogram here. Okay, and this parallelogram is basically like an approximation of the corresponding the shingle here. Okay, so roughly speaking, this thing here, RU delta U cross RU delta V, the magnitude of this thing is going to be the area of the corresponding shingle on the surface. Okay. And then you sum all these, this thing. Is basically like you're summing all the areas of the shingles to get the area, the total surface area. So that's just to give you some sense of what's going on. Right, because remember, what's the cross product? What's the magnitude of the cross product? The magnitude of the cross product is the area of the parallelogram, right? The area of the parallelogram that is spanned by these two vectors, right? So you got this vector and you have this vector here, right? You take the cross product, you take the magnitude of that, you get the area of this parallelogram, right? And as you get smaller and smaller, then the better this parallelogram approximates the shingle. So as it goes to infinity, right? As it goes to infinity, it gives you the best approximation. Okay, so next thing we're going to talk about. Any questions? Any questions? Next thing we're going to talk about are integrals on surfaces. So we have surfaces now. We can take areas of surfaces. And now we're going to talk about the integral of a function on a surface. Okay. So given a continuous function f from S to R. Okay. So, actually, let me go backwards, sorry. So you have some surface, so let S be a surface parametrized by some R of UV, giving you XUV, YUV, ZUV, and UV ranges over some domain. See a picture. Here's your D. R maps into some surface in R3. So then you have some function on S, and you want to talk about the integral of the function on S. Okay. So given a function f from S to R, so f, right, is a function on S, right, into R, right, associating some value to each point. We define integral of f on S sort of dissatisfying. Why should I use S in two meanings? Let me call this thing Chrysippus. Otherwise, it's sort of bad, very bad notation. We'll define this as f evaluated at RUV times RU plus RV dA over D. So the interpretation, right? Well, what does this mean? Right? This thing is the area of a tiny shingle, right? This thing is the area of some tiny parallelogram here, right? And then you're taking the function at a point on that parallelogram. Right? You're taking function's value at that point, and you're multiplying by the area of the base, right? So it's basically, you know, to every shingle here, you're calculating a volume. You're calculating a volume, right? And then you add up all those things. Or maybe it's better to think of this to think of f as a density function. Okay. So then what you're saying is that you're taking this little piece and then you're multiplying by some density, and this thing is going to be the mass of your object. That's probably better visualization. Does that make sense? Everybody see what I'm saying here? Right? You have this area, right? You have this area here, and then you're multiplying each of those areas by some number, right? And that gives you, if that's the density, then that gives you the weight of that little shingle, and then you sum up all those weights and you get the total weight. So let's do an example. It's pretty straightforward. It's not all that. It's basically just slightly more difficult than calculating surface area. So let's say that S is the graph of g of x y equals x squared plus y squared plus 3. Over the domain x squared plus y squared is less than 2. Okay. So you have this domain, you have this object, right? It's a circular paraboloid, and you're looking at it over this disk. Right? You have a circular paraboloid over this disk. You have part of a circular paraboloid over a disk, and you have a function given by f of x, y, z equals z minus x squared. Somebody says, I'd like you to calculate f against the surface area. This big S stands for surface area. You calculate the integral of f against the surface area over this surface. So I should call this, give this a name, the integral of f against surface area over the surface. So, you know, it's easy, right? You need a parametrization, right? You need a parametrization of this thing. Well, it's a graph, so you know what parameterization is going to be. That's going to be your parameterization. You differentiate, you take the tangent vectors along the grid lines, right? So 1, 0, 2x, 1, 0, 1, 0, 2y. You cross them. You get 0. Yeah, thank you. Yeah, something was very wrong. Thanks. Who's saying this? Thank you. Okay. So here you get negative 2x, and then you get negative 2y, and then you get 1. So the right. And then you just do the calculation. So f ds for the surface is going to be, so you need to take f evaluated. You take your function evaluated at the point on the surface. Okay? So f at r xy is going to be z minus x squared, right? So z minus x squared, z minus x squared. So you get y squared plus 3 times and then whatever you want as x over this thing. Okay. And then it turns into this integral over this thing. It turns out, if you want to do it, that it's best to do this using polar coordinates. If you actually want to do it. Okay. Any questions? Any questions? Anybody? No? Not exciting. Okay. So should I make you do another example? Do you guys want to do an example, or is it like so straightforward that you don't think it's necessary? Close your eyes. Raise a finger if you want to do an example. Oh, okay. Okay. Open your eyes. Everybody wants to do this. Almost everybody wants to do this. Yes, I shouldn't disparage the material. Okay. So here you have a parametrization. And it goes from this rectangle to something. Right? What is this a parametrization of? What is this a parametrization of? Multivariable.
Circle, radius, sphere, something.
Nobody's gotten it yet. Cone, yeah. Cone. Cone is it, right? Because you've got, if you chop it at height, if you chop it at a certain height, right? You see that the radius, you get a circle of radius that height, right? So if you chop it low, you're going to get a circle of small radius, and as you increase, the radii of the sphere increase linearly, right? Okay, so it's a cone. Right. So so and let's let m x y z be 2 square root of x squared plus y squared. And I'd like you to calculate the integral of m over this curve. I mean, over this cone parametrized by phi. Maybe I should call this S. It's a surface. Okay, so take 1 minute to set up the integral, or 2 minutes. Sorry, Glenn, just followed by your shirt.
Was Jack from Merrick's? Is that a Jack I was looking up for?
Yes. Okay. Okay, turn to somebody next to you and talk.
As far as I go to that was almost
When f of x, y, z isn't what goes into the
Is that superficial situation?
Yeah, so I'll get back to
Okay, yeah, so that is a vector.
That's a vector.
Okay, that's why I got confused, because I was trying to then put it into.
Okay, okay, so what do we need to do?
Yeah. Okay.
So we need to take phi's derivative with respect to r, right? We get cosine theta, sine theta 1. Phi's derivative with respect to theta, we get negative r sine theta, r cosine theta, 0. Then take the cross product. You end up with negative r cosine theta. Negative r sine theta, and then r, right? And m evaluated at phi r theta is of course going to be 2 times the square root of r cosine squared, r cosine theta squared plus r sine theta squared, so it's just going to be r squared. 2 epsilon. And so the air, this thing, m ds over the surface is going to be 2 absolute value of r times the magnitude of that thing, right? The magnitude of that is going to be the square root of this squared plus that squared, but that's r squared again, right? Plus r squared. Theta, as theta goes over 0 to 2 pi, and r goes from 0 to 1. Right? So you can get rid of those things, and you get 2r squared, right? So you get 2 square roots of 2r squared dr d theta, 0 to 2 pi, and 0 to 1. So you get 1/3 times 2 pi. Very cool. Okay. Any questions on how to integrate functions? It's